Okay, hi everybody. So, yeah, as mentioned, I'm originally from Canada. I now live in Tokyo, and so for the Japanese people in the audience, I like to explain that I have learned I have a Japanese name. If you can't read the Chinese characters, find someone who thinks that's funny in the audience and use it as an icebreaker at the next coffee break to see why my name is ridiculous in Japanese. So what I'm not going to be talking about today, so I was asked to talk about HPC challenges in astrophysics, but that's of course an enormously broad field. I am specifically working in observational gravitational wave astronomy. And there are actually a lot of people here, the students, the attendees, with projects in this field. So you should go and talk to them if you want to learn about PDE solvers. So for example, simulations of space-time itself or electrodynamics in general relativity, simulations of matter under extreme conditions. N-particle solvers, I'm not going to be talking about those. So that's, for example, cosmology or planetary disk simulations, orbital dynamics. Radiation transport codes are very important. This made news recently with the photograph of the plasma around a black hole. So the interpretation of those images relies heavily on this sort of stuff. Understanding the equation of state of neutron stars requires computational quantum mechanics. And then the gravitational wave detectors themselves are extraordinarily complicated systems. The LIGO detectors each have 300,000 data streams coming out of them. That's the control system. So there's sensors everywhere, there's actuators everywhere, and it's an extremely complicated control system that's used to stabilize the detector using all of those things. So I'm not talking about control system theory at that scale either. All of this stuff, though, does have to be brought together to understand something like this. So this is a computer simulation from the BAM collaboration. It's showing the collision of a pair of neutron stars. These objects are about 20 kilometers in diameter, and this is not real time. They're orbiting at several hundred hertz in real time. And everything is here. You've got space-time effects, you've got matter effects. Putting this all together and then detecting it with a ground-based detector requires all sorts of computational technology to be brought together. So we're not talking about any of that. We're going to talk about just the detection problem for gravitational waves themselves. So what is a gravitational wave? A gravitational wave, you can really think of it as the space-time analogy of an electromagnetic wave. In electrodynamics, when you move charges and currents, you can produce a wave of electromagnetic energy. And general relativity, or our theory of gravity, says the same thing about space-time. If you move the charges of space-time curvature, so that's masses and currents, or momenta, then that can lead to the radiation of waves of gravity, so waves of space-time curvature, just like in electrodynamics. And those waves carry energy, so they have an effect on the system that's emitting them. So the dynamics of the system are altered by the emission of the gravitational waves. And the canonical example is a spiral pattern of gravitational waves produced by orbiting masses, just like that computer simulation on the previous slide. But there's this fun YouTube video you can look. So this is a sheet of Lycra and a drill doing a remarkably good.
When LIGO and
all right. So why do we want to find them? Because they are produced by different physical processes than produce electromagnetic waves, they carry different information about the sources that produce them than the electromagnetic radiation from a source. They are also very weakly coupled to matter. Gravitational waves basically pass through absolutely everything is transparent to gravitational waves, with the one exception of black holes, which are not transparent to anything. So because you can see gravitational waves through dust clouds, they pass right up through the Earth, no problem. You can learn things, you can learn novel things about parts of astrophysical systems that are inaccessible through other probes. Unfortunately, because they are, everything is transparent to them, anything you might try to build to find them is also transparent to them. So detecting them is extremely difficult, and it's taken a heroic effort over many decades to find them, but it was finally successful. And the technology that finally did it was the laser interferometer. So this is sort of a cartoon depiction of a Michelson interferometer. Real ones are much bigger. This is an aerial photograph of the LIGO Livingston detector. These arms are 4 kilometers long, and there is on the order of 1 million watts of laser power circulating in them. So this is what is this, a 1 milliwatt laser? So, a lot more. So neutron stars, I've mentioned that before. I know there's a lot of people who are not from this field, so I'll go into a little bit of detail there. These are the collapsed cores of massive stars. They have a neutron star will have a mass of about 1.5 times the mass of the sun. They range from maybe 1.4 solar masses, 1.3, up to maybe 2 or 3 solar masses. We don't know how heavy they can be, but they're crushed down to it's the densest state of matter next to a black hole. So the material is just on the edge of collapsing into a black hole. So even though they're extremely massive, they're very, very small. And this is a scaled diagram of a neutron star on top of a map of Tokyo. So they are, it's really hard to wrap your head around this. You'd have this object that's kind of that size, but weighs more than our entire solar system. And again, if a pair of them collide, because they're so small, they can approach very close to each other. So the orbital speed just becomes enormous. So again, in a simulation like this, the collision occurs at an orbital frequency of close to 300 hertz. So if you were actually seeing this system, it wouldn't look like this. They'd be going around so fast that your eyes could not see them. They'd just be a blur. It would look like this blurry torus of matter rapidly shrinking down to a collision. You would not be able to see them as distinct spherical objects going around in a circle. So on August 17th of 2017, we detected the gravitational waves from a collision of a pair of neutron stars. This is an artist's depiction of what the computer simulation was doing in the previous slide. This is actually, I believe, in the public domain, so you can download it and use it everywhere you want. It's awesome. The first report of this event was a flash of gamma rays from the Fermi satellite. And then a gravitational wave signal was observed in the data shortly after. This is a time frequency plot of the signal. So it's this swept sinusoidal signal in the data. And the end time is kind of at 0 here. This laser pointer's about to die. Let me see what I can do. At 0 seconds. So you can get sort of a sense of the rate at which this chirp evolves. This feature in the data, this is dead. So this feature in the data is 2 seconds before the flash of gamma rays that were reported by the Fermi satellite. And about 10 hours later, because we could identify the sky location approximately, people with telescopes were searching for a flash of light, and a photograph was taken. This is the first one that was taken, but then almost immediately, many people were able to take photographs of this object. So this is a reference image from the Hubble Space Telescope about a month before, or a couple of months before, in April. And there you see there's an extra dot there. And studying that dot of light, indicated it to be consistent with the kind of light you'd expect from this sort of a collision. And that then launched this enormous follow-up campaign. And this paper here describes the first 10 days of observations of this source. This paper has 3,600 authors on it. The International Astronomical Union has a membership of about 12,000. So approximately a quarter of all of the astronomers in the world are co-authors of this paper, which kind of gives you an indication of the significance of the discovery to the astronomical community. But one of the keys was finding it quickly. If it had not been identified until weeks later in some sort of slow offline analysis of the data, the flash, that optical transient that you see in that photograph, this thing down here, it would have faded out of view, And the precise location of the source would not have been identified, which means we couldn't have done things like, X-ray follow-ups and radio follow-ups with facilities that have very, very narrow fields of view and can't really find the source unless you know exactly where to look. Oops, I went backwards. Okay, so what's going on behind the scenes that enabled this? Gravitational wave antennas, they're like radio antennas. I don't know if that helps much, but they provide a digitized record of the projection of the field strength on the antenna. So they're not like a photographic telescope. They provide an actual time series record. No real detector has infinite bandwidth. So there's always some low frequency cutoff and a high frequency cutoff. And you can see frequencies in between, but nothing else. So for ground-based detectors, those frequencies are limited by seismic noise, so ground motion at the low frequency end, and then quantization of the laser field at the high frequency end. And as you saw, the compact object merger signals are these kind of sinusoidal signals that are tracking the orbital evolution of the system as a function of time. So they start out at low frequency when the objects are orbiting slowly, and the frequency ramps up as the orbit shrinks and the objects collide. So the data looks something like this. This is actually a random number generator that has the same statistical properties as the data. It's not real data. On long time scales, so this is hundreds of seconds, it looks like just stationary Gaussian noise. It is stationary, but it's colored noise. So there are correlations in it. If you zoom in, you start to see structure, and you can see these kind of low frequency oscillations in it. And this is, again, seismic noise and sort of 60 hertz harmonics from the power grid interfering with the data. It also has long duration fluctuations in it. So this is a movie of the spectrum over some period of time. You can see the timestamp on the top. We'll just speed it up here a bit. So it's going much faster than real time. And you can see it's pretty stable, but there are features that are moving up and down. So this is, what you're doing is you're looking at this kind of random time series data that has these sorts of natural fluctuations in it, which you have to kind of remove or normalize out. And you're looking for signals that look like this. So again, it's a swept frequency sinusoidal function. And this is what it sounds like. As I mentioned, the orbital frequency for neutron stars is in the hundreds of hertz, so it's right in the audio band. You can listen to it. So you have to try to imagine like objects the mass of the sun going around each other hundreds of times a second and then smashing into each other. This is the sound of 170817. So this is the detector noise. The signal is already going, and close to this time, the analysis system has already identified that a signal is present. You can't hear it yet, but the computers know that it's there. And I don't know if I can get this. I'm at a funny angle here. What's it say on the other side? You won't be able to hear it. I can't see that. Normally I'd be able to tell you when to listen, but I'm having trouble seeing because of the aspect ratio. Okay, never mind. So how do we find these signals in the noise? This is an animation that you can find on YouTube. So you've got noise, and you've got this template, and we just keep computing an inner product between the noise or the data and the template waveform. And as time goes by, this inner product goes up and down and up and down, and every once in a while there's a spike. And that's a possible signal, right? So that's what we want to do. We want to compute this. We've got this time series data. We want to compute an inner product with a template waveform and just kind of repeat that as a function of time until we find something of interest. Okay, but we don't have just one waveform we're looking for. There's many kinds of waveforms. So this is a sort of a depiction of the template bank used for the O1 search. So this was the analysis that made the first discovery of gravitational waves in 2015. So this is kind of old technology now, where we've used much bigger template banks. There's 249,077 waveforms in here. They're color-coded by the range of spins that the systems are allowed to have. So this chi parameter, this is the mass-weighted projection the spins of the objects onto the orbital axis. That's the dominant contribution to the waveform structure. You can get this out of Sarah Cottle's paper on techniques for gravitational wave detection of compact binary coalescence in the proceedings of the 26th European Signal Processing Conference. So if you want to get more information about the analysis techniques, that's a good place to look. Okay, so now the rubber hits the road. Okay, so LIGO's data is double precision, sampled at 16,384 hertz. Virgo's are single precision at 20 kilohertz. They say they're metric, so they don't use powers of 2 in Europe. The compact object merger template banks, as I said, they have 250,000 templates in 01. Modern ones are up to 600,000, and they just keep growing. So it's sort of on the order of 1 million templates. The longest waveforms that we search for are on the order of 10 minutes. So that 1708-17 neutron star merger, that was a 5-minute long waveform. So at the sample rate, you're looking at order of 10 million samples. So when you take this inner product, that's the size of the inner product you're doing. So a naive brute force estimate for the number of calculations required to do this is you need something like 10 to the 18 floating point multiply-add operations per second sustained in order to do this analysis. Now you say, okay, but that is stupid because obviously nobody does n-squared inner products like this. You use FFT convolution. That's fine. FFT convolution, yeah, it knocks 6 orders of magnitude off the cost of that, which is fantastic. But then you're just down to 10 to the 18. So you still need order of petaflops to sort of do this, and that's sustained horsepower, not peak. You need to just average over, computer failures and so on if you want to keep up with the data. And if you don't find the signals quickly, then you miss that flash. You don't provide enough opportunity for optical telescopes to go and find the signal. So this 10-minute long waveform, we actually have to report its presence within seconds. So again, you might naively say, oh, well, if you just throw more computers at it, you can do it faster. But and then as an extra bonus, you might also care how sensitive your analysis is. So you want to do it again with hiding fake signals in to see which ones you can find. So the total cost is enormous if you just do it all naively, which means you cannot solve this problem by just coding up a prototype serial algorithm, like doing a little program on your laptop, testing it, debugging it, and then buying a room full of computers and parallelizing the whatever out of the code. It does not scale that way. You have to, horsepower can't solve this, and optimization can't solve this. Factors of 2, factors of 3, 10% are not going to knock, the 6 orders of magnitude off that you need to actually do this with a reasonable budget. So you have to start from the beginning. You have to understand the scale of the problem from the start, and approach it from the perspective of a massively parallel calculation. You have to sort of think about how to actually do that efficiently. And in particular, you really have to change the question. You have to say, look, we're not going to do double precision accuracy inner products. We don't care about 17 significant figures. We don't care about, there's stuff we don't care about. We really just want to know that we can find the signals. And so there's a lot of tricks, right? So you also know a lot of things about the waveforms. They all look the same, kind of. The frequency changes a little bit. So you can start using tricks, right? So you slice them into time domain fragments, and the early parts you encode at a lower sample rate. You don't need them at 16 kilohertz. You can get away with 32 hertz sample rates at the early parts. So for hundreds of seconds at the start, you only need 10 samples per second for the waveform. So you slice them up in the time domain. Each of these fragments, you take the template bank, and then you do a singular value decomposition to sort of create an orthogonal basis that approximates the shape of the waveforms in those fragments. And they all look like the same sinusoid. So that provides a really high compression ratio. And then you have to reassemble it all. So you take all of these little fragments, and you put them all back together. And that's a huge data management mess. So we used an off-the-shelf signal processing framework to put it all together called Gstreamer. And this is kind of a graphical depiction of how it works. You've got data coming in, it's teed off and downsampled to different sample rates. Then we've got the orthogonal basis vectors from the singular value decomposition being convolved with the data. And then we have linear combinations of those being computed to reconstruct the original match filter signal to noise ratio for each of the fragments. And then those are upsampled and reassembled to get the original numbers that we were really interested in, but kind of only approximately. Like we've lost some accuracy. We're only reconstructing them to 3 or 4 significant figures, not 17. But it's very fast. And so this is kind of a depiction of what the chart actually looks like if you make a graph of the Gstreamer pipeline. So these little green boxes are signal processing elements. They're amplifiers, so like something that scales the samples by a number or changes the sample rate or adds 2 streams together, like a thing right here. We've got 2 streams coming together. They're being summed. That's a summing operation. So that's kind of the scale of these green boxes. And you can see how many of them there are. If you zoom in on this plot, it looks something like this. It's been years since any human understood what was going on here. This graph is machine generated from the template bank itself. So it's fed into a computer, which does this sort of optimization. It identifies where the slices should be put. It does the singular value decomposition, and it comes up with a plan for how to do the filtering, which is represented in these charts. So all of that, what I've described, that whole process, that's just the system to scan the data and identify the candidate signals. Okay, what we call what we call candidates. They're like that first animation. It's the spike in this inner product that we're computing. Those aren't necessarily signals. The next thing we have to do is decide which ones of those are actually interesting. Because if somebody drives a truck past the antenna, then you'll get spikes in the signal-to-noise ratio too. And those are not, that's just noise. So you have to look more carefully to decide whether they're interesting or not. So each of the templates in the template bank, we set a threshold so that they report approximately 1 candidate per second. And again, remember, there's order 1 million templates. So the candidate rate coming out of this first stage of the system is a megahertz. And for each of those, we have to decide whether they're interesting or not. And then it just goes on from there. Once you've got your things that you believe are signals, then from those, you want to do more Bayesian inference of the astrophysical event rate, the compact object mass distribution, neutron star equations of state, all sorts of things. So I'm not going to talk too much about how we do all of that stuff. Just some of the mistakes that were made along the way. One of the mistakes was that it was vastly underestimated how much computing would be required to do this. And there's this kind of the joke that people point to is one of the early proposals for LIGO explained what the computing plan was. This was literally the computing plan for the gravitational wave experiment. The control room would have a dedicated workstation to identify interesting fragments of data. Remember, the identify interesting fragments of data is literally just what that green chart was doing. It's not picking the signals, it's not doing any of the astrophysical interpretation, it's just saying, oh, here's something interesting, here's something interesting, here's something interesting. And you need, anyway, so this was, of course, people who are old will remember when a dedicated workstation sounded like a lot of computers, but it was still way off the mark. The other problem was that there was kind of this Boeing style of software engineering that was taken at the beginning, where you write a spec, you hand the spec to the programmers produce components which are then integrated, and you'll find gravitational waves. And that didn't work because really the problem was we didn't know how to find gravitational waves. We had to try different things. We weren't sure until the detectors were being built and operated, what kind of noise we were going to have to mitigate. So you needed to sort of, you needed to have do-overs, and this wasn't really amenable to that. We really suffered very badly from not invented here syndrome. So if you go through the version control system, you can find that in the early days, we were writing our own FFT code. We were writing our own random number generators. Even debugging software, we were doing our own call tracing in the library. It was just completely absurd. And people justified it. They would say, oh, but then you have control of the source code, and then you can fix it if there's a problem, and you know how it works, and so on. Well, of course, anyway, I'll get back to that. There's also hubris. It will take me less time to just write it myself than read the manual. It's kind of this assumption that if somebody else has done something, it must have been trivial. Only I do complicated things. And so, this was very bad. This reluctance to ever open a manual and just learn how to use an existing solution. There was also over-design, and I like to pick on the LIGO Virgo frame file specification. This is what we call the data format that our files are stored in, or the time series from the detectors are in. to this day, and I'm not kidding, literally nothing can read the format. You can load them into memory, and you can extract all the vectors and all the things. But if you go through the spec, you can attach a nanosecond resolution offset to a vector. You can attach units to a vector. There's auxiliary vectors that tell you which samples are valid and which ones aren't. And no one knows what goes in those fields. No one knows how to, the units is just a free-form string. Well, what's the encoding for that? How do you, is it METRE for meter, or is it just M? There's no library. There's just libraries to get it in and out of memory, but not to say when a file is correct or not correct. Also, there's I just need MATLAB. I can do all of this with MATLAB, and that really leads to this. We say in English, if your only tool is a hammer, every problem looks like a nail, and there was a lot of that. So what worked? Well, I mentioned the need to be able to have do-overs. So Agile Development. We really didn't know how to find signals, so we needed to be able to quickly reconfigure the software and try again. So that proved to be much more important than just getting raw performance out of the system. Being able to, have second attempts. And so that's where, we find that Python and SQL do have a place in HPC, at least in our world. I know some people here are opposed to this, but we've got a Python and HPC guy at the back there. The free software community participation. Okay, don't fix bugs, add features, and then keep the result in your home directory. All right, you really have to share your fixes, push them upstream so that the next version will have your fixes in, and you don't have to keep repatching the software locally. Use existing software wherever possible. Don't write your own FFT routines. Don't write your own matrix inverters. Don't, take the extra time to research what is available, even if you could write it just as quickly as reading the manual. You probably haven't fully appreciated some of the subtleties. The problem will probably be more complex than you understood at first. Yeah, so just take that time. Don't over-design stuff. So the LIGO Virgo frame format, all we really needed was time series in a file. So if we had just tarred up .wave files, audio files, that actually would have provided all of the features we've ever used from this format. Plus, no one would have had to write a single line of code because that's all already written. Also, when you're looking for existing solutions, make sure it's actively maintained. Don't pick something that has had no releases in 5 years. Just check to see whether people are keeping up to date. And then you keep up to date. So pay the price of tracking upstream API changes. Don't say, okay, I've got my solution, it works. Oh, they've changed the code. I don't want to have to change my code, so I'm going to just freeze myself in at this version and never change. It's worth tracking the API change. Even if you don't see that it's adding any features, by removing the need for you to maintain your own versions locally, that saves you a lot of time. So time to roll the credits. The Gravitational-wave Open Science Center, you can go there to learn more about what we're doing. The LIGO algorithm library, you can go and see the commit history. You can go and find how we did call tracing and so on way back. The GST LAL system, this is the Gstreamer plus LAL LIGO algorithm library. You can find its Git there. And then we've also, of course, made, in no particular order, use of all kinds of different free software projects, Python, Gstreamer. QHAL is completely magic. I don't know if anyone's used it. I don't know how it does what it does. But anyway, it's amazing. All sorts of stuff. And even Kafka. Don't ask. Okay, thanks.